Leveraging mutual information for asymmetric learning under partial observability. Hai Nguyen, Long Din, Robert Platt, Christopher Amato, Khoury College of Computer Sciences, Northeastern University, Boston, MA, United States. Horus AI, Hanoi, Vietnam. Abstract: even though partial observability is prevalent in robotics, most reinforcement learning studies avoid it due to the difficulty of learning a policy that can efficiently memorize past events and seek information. Fortunately, in many cases, learning can be done in an asymmetric setting where states are available during training but not during execution. Prior studies often leverage the state to indirectly influence the training of a history-based actor, actor-critic methods, or a history-based critic, value-based methods. Instead, we propose using state observation and state history mutual information to improve the agent's architecture and ability to seek information and memorize efficiently through intrinsic rewards and an auxiliary task. Our method outperforms strong baselines through extensive experiments and achieves successful sim-to-real transfers to a real robot. Keywords: partial observability, mutual information, asymmetric learning introduction. While partial observability is ubiquitous in robotics, most reinforcement learning (RL) robotics research avoids it due to the difficulty of training a policy that can effectively memorize past information and perform information-gathering actions. Fortunately, full or near-full observability during training is possible in many real-world domains using a simulator or a generative environment model. In the literature, this is the asymmetric learning setting, in which privileged information, such as states, can be available during training. Previous work in this setting often learns a state-based critic to indirectly influence the learning process of a history-based actor using actor-critic RL to output actions directly, or b, a history-based critic in value-based RL to extract actions from. In contrast, using an information theoretic approach, we instead use the state to generate intrinsic rewards and optimize an auxiliary task, shaping the agent's behavior directly. Specifically, this study proposes to use the mutual information between the state and the history during training to motivate active information gathering and to improve task-relevant memorization. Our intuition is that active information gathering mainly involves discovering actions that help the agent reveal more about the environment's state, gradually moving from partial to full observability. Therefore, the amount of mutual information gained per step can be a useful intrinsic reward to encourage informative actions. Moreover, we train the agent to predict the state features from past histories as an auxiliary task to help the agent focus on memorizing enlightening past events, i.e., previous actions or observations that have gained more information about the environment state. We propose a two-stage approach to turn intuition into a practical and efficient method. The first stage extracts task-relevant but non-overlapping state and observation features by performing supervised learning using a state-contained dataset. Specifically, we predict the reward and the dynamics in the feature space while minimizing the mutual information between state and observation features. We perform task learning in the second stage, which involves training a transformer-based sequence model to output a history summary with maximal mutual information with the learned state features. The goal is to reduce the memory burden of the sequence model by encouraging it to avoid memorizing readily available observation features. With a purposefully designed structure, intrinsic rewards, and the auxiliary task, our approach outperforms other strong baselines in experiments on 6 domains. Moreover, we carry out successful sim-to-real transfers to verify that the policies learned in simulation can perform well in 3 robot manipulation tasks. We first discuss the partially observable Markov decision process, POMDP framework, methods that maximize the mutual information, and describe our problem statement. A POMDP is defined by a tuple SATRO, where S, A, and O are the state space, the action space, and the observation space, respectively. In a POMDP, the transition function TAS governs state changes, and the observation function OAO controls how observations are emitted. Acting optimally in a POMDP with a high level of partial observability often requires information gathering and a memory-based policy that selects actions based on the entire action observation history, HT equals 080 AT-1 OT. Mutual information MI measures the dependence between two random variables x and y. I equals e pxy, left frac xy, px py, right. Minimizing MI, Cheng et al. Proposed to minimize MI by minimizing an upper bound named contrastive log ratio upper bound club, which is formulated as I club equals e xy log p mec x e p log py mid x g I xy. In practice, py mid x is often unknown and approximated by a learnable variational distribution, qy mid x. Maximizing MI deep info max dim is a method that maximizes the MI between x and a high-level representation zx of x. The process involves an encoder exzx and a classifier x-zxr to discriminate between samples from pxzx and the product of marginals pzx. DIM uses the Jensen-Shannon MI estimator, I dim p equals ex minus sp minus sigma x e x px px p x ex. Maximizing IXZX involves continuously updating E and SIGU by maximizing the estimator through gradient descent. We focus on the asymmetric RL setting in which, during training, both the state and the observation OT are available while only OT is accessible during execution. The goal here is to find a history-based, not reactive, policy P at HT which maximizes the expected discounted return gamma of T RFT. Our method has two stages. First, we learn non-overlapping state and observation features from a fixed dataset containing privileged state information. The dataset is generated using a random agent. After a simple hard-coded planner, we train a memory-based agent with a two-branch architecture using intrinsic rewards and an auxiliary task. Learning task-relevant and non-overlapping state and observation features. This stage is about learning state features encoded by a state encoder fui and observation features encoded by an observation encoder pass with two properties. Firstly, concatenated features ZO encodes task-relevant state features. Secondly, ZSTO contain unobservable task-relevant features, while ZO contains observable task-relevant features. With these properties satisfied, ZS will encode only unobservable task-relevant features inferred from the history, while ZO already contains features from observations. To satisfy the properties, we train ZS ZO to be predictive of ZS, ZO, and the reward R. For the second property, instead of minimizing the KL divergence between phi S and a standard normal distribution, we minimize the mutual information IZZO using EQ2. To further regularize learning, we maximize IOZO and IS as per EQ3. Dataset DAIRI AIOI NI=1 is required, and the algorithm involves several steps to update the features and maximize various information metrics. Learning partially observable tasks. After learning ZS and ZO, a memory-based agent with a two-branch architecture is introduced for RL task learning. The top branch encodes history using a GPT-v2-based sequence model, while the bottom branch encodes the current observation. The architecture aims to alleviate memory burden by having non-overlapping ZS and ZO and focusing only on unobserved features in ZS. Encouraging information gathering is done by rewarding actions that maximize IHTZST and using this as an auxiliary task for memorizing important information from history. Our proposed agent structure has two branches where the observation encoder, denoted as PAS, is directly used for the bottom branch. An intrinsic reward encourages information seeking by maximizing the mutual information IHT-ZST to gather maximal information with ZST. The lower bound for maximizing mutual information is defined as I8-ZST equal H of ZST minus ZST HTZ plus EHT pi log F ZST plus log F thus TH neuro plus ET minus 1xt equals 0 log F the THT1, where F though H predicts ZS with a Gaussian distribution with variance ρ2i. The intrinsic reward term intrinsic T captures incremental information gained between the current and previous history, calculated by intrinsic T equals ZST F though HT minus d cosine ZST FFHT minus 1. Additionally, we train the top branch K to predict ZS over episodes to encourage information retention using the same EQ, with K instead of F. This training method indirectly maximizes IVH-ZS for the agent important events in history. Several previous works have leveraged privileged information successfully in policy learning, particularly in multi-agent settings. For single-agent settings, different approaches utilize the state availability or auxiliary losses to improve policy learning under partial observability. Some methods leverage state access or history-based critics within the actor-critic framework to enhance learning performance. Other related works also explore utilizing informational rewards to incentivize information gathering. Goal, movable, immovable, immovable, movable, goal pad, goal, drawer opening, block pulling, block pushing, heaven, hell, sphinx, car flag 2D, heaven, hell, goal locked, unlocked. Domains, discrete continuous actions, vector-based, pixel-based observations. While these methods use privileged information as additional input for training a critic, we find a compact and task-relevant representation of the privileged information, similar to prior work. We diverge by using privileged information directly to promote information gathering. Our information-based approach shares similarities with a meta-learning work, which uses mutual information between history and training task ID to calculate intrinsic rewards for encouraging information gathering. While other work learns two policies for exploration, using intrinsic rewards, and exploitation with environment rewards, we learn a single policy using a combined reward and add an auxiliary loss to enhance memorization. Our idea of minimizing the overlap between ZS and ZO connects with a mixed observability framework that eliminated overlap between state and observation to reduce computation for state distribution tracking. However, the proposed method requires complete knowledge of dynamics, planning-based, and state and observation structure, while ours assumes no such knowledge. Simulation experiments. We conduct experiments on 3 grid world domains with discrete action spaces and 3 robot manipulation domains with continuous action spaces. See more details in Appendix B. Discrete action space domains. In Sphinx, car flag 2D, and heaven hell, an agent must reach a randomly generated goal position. Specifically, the goal can be one of the green corners in Sphinx, left-right ends in heaven hell, and any cell in car flag 2D. Normally, the observation only includes the agent's location. The agent can observe the goal additionally only when entering the information region. In Sphinx and car flag 2D, the observation encodes the goal cell when entering the blue region. Rewards are sparse, +1 for reaching the goal, -1 for reaching trap locations, if any, and 0 otherwise. In Sphinx, an additional penalty of -0.2 is imposed when entering the blue cell, making the information gathering process costly. These domains encode both the current observation and the goal cell in the state. Continuous action space domains. In block pulling, block pushing, and drawer opening, adapted from domains in literature, a robot must interact with the only movable object among 2, which appear the same under a top-down depth camera. The mobility of the objects is not apparent from the current depth image, the observation. An optimal agent must take information gathering actions to determine the object's mobility and then retain this information while manipulating the movable object to complete tasks. The state is pixel-based, created by combining the observation with a one-channel image that masks everything except the movable object. A reward of +1 is given only upon task completion. To address reward sparsity, 80 episodes of demonstrations are provided to pre-populate the replay buffers of all agents. Furthermore, due to spatial symmetry in these tasks, random SO2 rotations are used consistently for all observations and actions within an episode for data augmentation. Baselines we use DDQN, discrete action spaces, and SAC, continuous action spaces, as the base RL algorithms for our agent and all baselines. We make them memory-based using a simplified version of GPTv2 as the sequence model. All following baselines use the 2-branch architecture like ours. DTQN, TSAC, these variants are based on DQN and SAC and use a transformer, a simplified version of GPTv2 as the sequence model. ZPDRQN, ZPRSAC, Nye et al. Proposed the next hidden state prediction as an unsupervised auxiliary task to improve learning under partial observability. We applied their method to DRQN and RSAC and used a GRU instead of a transformer here to satisfy the recurrent encoder property, i.e., a transformer is not a recurrent model. BADTQN, BATSAC, the biased asymmetric version of DTQN and TSAC. For BADTQN, QSA and QHA are learned during training, and argmax, a QHA, is the selected action during deployment. For BATSAC, only the state-based critic QA is learned to help learn a history-based actor. These asymmetric agents can sometimes perform well but were found to introduce learning bias, i.e. QA is a biased estimate of QHA. UA-DTQN, UA-TSAC, we implement unbiased asymmetric variants of DTQN and TSAC using the framework proposed, originally applied to DRQN and A2C. To fix the bias issue, during training, these methods learn QHSA instead of QAHA and use QHA to pick actions during execution. BDQN, BSAC. Believer originally trains a Khoury-based history encoder, similar to our first stage. For a fair comparison, we use the same GPT to replace the GRU and the same dataset for our agent and these agents. Because the encoders already encode the history, their outputs are directly used for memoryless RL algorithms, i.e. DQN or SAC in our case. Furthermore, we fine-tune the history encoders to strengthen these baselines following the public code. Environment, step 0.4 to 20.0, 20.40, 60, 81.0. Return DTQN, BA, DTQN, UAZP, DRQN. Hours A. Sphinx environment, step 0.0, 2040, 60, 81.0. Return DTQN, BA, DQN, UA, DTQN, ZPDR hours B. Carflag 2D environment, step 0.5, 0.25, 1051.21.5. Return DTQN, BA, DTQN, UA, DTQN, BDQN, ZPDRQN hours C. Heaven Hell environment. Step point 20 40 60 81. Return P UATSAC BSAC ZPRSAC hours. D block pulling environment. Step 0.04 60 881.neuro. Return TSAC BA TSAC BSAC BSAC ZPRSAC hours. Block pushing environment. Step 0.0.40.60.81.0. Return TSAC BA TSAC UA TSAC BSAC ZPRSAC hours F. Drawer opening learning curves averaged over 5 random seeds with shaded mean and 1 stead. Dashed vertical lines denote when the task learning stage of our method and BDQN BSAC starts. Experimental results. As shown in Fig 3, our method is generally superior to all baselines in all domains. Among baselines with state access like ours, only unbiased asymmetric methods can compete with ours in Heaven Hell, block pulling, and drawer opening. Most surprisingly, believer-based baselines do not perform well in all domains despite our significant effort to strengthen them, replacing GRU with GPT, hyperparameter tuning, and online fine-tuning. When information seeking is hard, e.g. in Sphinx with a clarifying penalty or in Heaven Hell with 6, test structure environment, step return hours, ZS only, hours environment, step return, ZS only, believer, ZS only, believer. Figure 4, overlapping test, using ZS or concatenating ZS and ZO for task learning. Learning curves in Heaven Hell when using our method or believer to learn ZS and ZO. A goal-avoided path for goal information. Only our agent can perform well by using the intrinsic rewards. When the information seeking is easier, our method still outperforms, e.g. in Carflag 2D, block pulling, and drawer opening, thanks to pre-trained compact features, learned high-quality, and non-overlapping representations. To show that our method can achieve both P1 and P2 in Section 3.1, we perform task learning in Heaven Hell using ZS or only ZS and raw state S. We compare 2 ways to learn the representation, our method and believer. From Fig 4, ZS yields better performance than the raw state. This indicates that our method can learn high-quality state features. As expected, using ZS alone fails to solve the task because ZS will only contain the features of the goal's position. The task can only be solved with the aid of ZO, which contains the agent's position. In contrast, when using believer to learn ZS and ZO, using either ZS or ZS makes no difference. Both can solve the task, indicating ZS also contains the agent's position, which is already contained in ZO. Ablation studies. In this section, we perform ablation studies to analyze our key design choices, using GPT instead of a recurrent neural network, e.g. a GRU, as the sequence model, and using both the auxiliary losses and the intrinsic rewards. We only report representative results in this section. See the Appendix D for more details. Environment, step return GPT, GRU Carflag 2D, environment, step return GPT, GA block pulling, environment, step return GPT, GRU block pushing. Comparing when using GPT or a GRU as the sequence model in our approach. Using GPT instead of a recurrent neural network. While a GRU might have trouble memorizing important information in long sequences, a GPT can attend to and memorize any past information. This property is crucial for our agent to maximize IHVS effectively. From the performance gap, we can see the important role of GPT. Using both auxiliary losses and intrinsic rewards, While the auxiliary losses help information retention, intrinsic rewards are needed to encourage information gathering directly. As shown in domains when information gathering is not challenging, such as in CarFlag 2D, and the robot domains, using auxiliary loss is sufficient for good performance. In Sphinx, when information is harder to seek because of the involved cost, the intrinsic rewards are essential to improve the performance. Environment step return intrinsic only, auxiliary plus intrinsic. Sphinx environment step return intrinsic only, auxiliary plus intrinsic. B. CarFlag 2D. Environment step return intrinsic only, auxiliary plus intrinsic. C. Block pushing 6. Comparing using intrinsic rewards or auxiliary losses versus using both. Sim to real transfers. Camera 1, Camera 2, Camera 3. Figure 7. Real robot setup. Domain Rs UA TSAC block pulling, block pushing, drawer opening, Table 1. Average success rates of sim to real transfers between our method and UA TSAC. To verify the performance of the learned policy in simulation, we perform sim to real transfers using the best policies in simulation to a UR5 robot. To best obtain non-occluded top-down depth images, we combine the point clouds from 2 side view cameras and 1 top-down camera and project at the gripper's position. Furthermore, during training, we add Perlin noise to the observation to reduce the gap between the simulated and the real-world depth images. We perform 50 evaluation episodes, divided equally into 2 cases when the policies first manipulate the immovable or movable objects. Results from Table 1 show that the learned policies can be zero-shot transferred in the real world, and our method performs better than the best baseline, UA TSAC. During sim-to-real transfers, the main failure mode is when the robot goes down to perform actions. Collisions with objects, e.g. blocks, drawers, might happen. This can trigger the robot's protective stop and terminate the episode. Additionally, in drawer opening, the transferred policies sometimes clumsily move one drawer far away from the other, creating a novel scene never seen in simulation. Conclusion and limitations. Conclusion. This work proposed an information-based method that directly uses the mutual information between the state and history to encourage information gathering under partial observability. We also tackle memorization by incorporating an auxiliary task to predict the state feature from the history to alleviate the agent's memory burden by only requiring its memory component to memorize unobservable task-relevant features. Experiments show that our method is effective and scalable to domains with high-dimensional states and observations with deployable working policies. Limitations. Our method's biggest limitation is the challenge of learning good and non-overlapping representations at the first stage. In practice, we need to select the right dataset to train with. We can use random interactions in the grid world domains, but expert demonstrations are needed for training in the robot domains so that the representations are useful. In practice, to guarantee the learned representations can satisfy both P1 and P2, we need to iterate between hyperparameter tuning and performing the overlapping test. We also want to note that while the second stage works optimally with high-quality representations, our method remains effective with less ideal features, as the agent can still refine these through reinforcement learning. Acknowledgements. This research is supported by grants from the Army Research Office, NASA, and the National Science Foundation. References: H. Kurniawati, Partially Observable Markov Decision Processes in Robotics. Annual Review of Control Robotics and Autonomous Systems, D. Shu and J. Pajaranen. Partially Observable Markov Decision Processes in Robotics, a Survey. IEEE Transactions on Robotics, L. Pinto, Andrich, P. Willinder, W. Zaremba, and P. Abil. Asymmetric Actor Critic for Image-Based Robot Learning. RSS, D. Chen, B. Zhou, V. Colton, and P. Kahenmel. Learning by Cheating. In Conference on Robot Learning, H. Nguyen, B. Daly, X. Song, C. Amato, and R. Platt. Belief-Grounded Networks for Accelerated Robot Learning under Partial Observability. In Proceedings of the Conference on Robot Learning, A. Bizarro, B. Daly, and C. Amato. Asymmetric DQN for Partially Observable Reinforcement Learning. In the Conference on Uncertainty in Artificial Intelligence, H. Nguyen, A. Bizarro, D. Wang, C. Amato, and R. Platt. Leveraging Fully Observable Policies for Learning under Partial Observability. In Annual Conference on Robot Learning, A. Wang, A. C. Lee, T. Q. Klassen, R. T. Akart, and S. A. McElraith. Learning Belief Representations for Partially Observable Deep RL. an international conference on machine learning, A. Bizero and C. Amato. Unbiased asymmetric reinforcement learning under partial observability. In proceedings of the International Conference on Autonomous Agents and Multi-Agent Systems, KJ Astrom, Optimal Control of Markov Processes with Incomplete State Information I, Journal of Mathematical Analysis and Applications, LP Kielbling, ML Littman, and AR Cassandra, Planning and Acting in Partially Observable Stochastic Domains, Artificial Intelligence, SP Singh, T. Jokala, and M.I. Jordan. Learning without state estimation in partially observable Markovian decision processes. In machine learning proceedings, P. Cheng, W. S. Dai, J. Liu, Z. Gan, and L. Karen. Club, a contrastive log ratio upper bound of mutual information. In International Conference on Machine Learning, R. D. Jelm, A. Fedorov, Esla Marchildan, P. Bachman, A. Trischler, and Y. Bengio. Learning deep representations by mutual information estimation and maximization. Arxiv preprint 108-0667 S. Nozin, B. Cheka, and R. Tomioka. FGAN, training generative neural samplers using variational divergence minimization. Advances in neural information processing systems. A. Zhang, R. McAllister, R. Calandra, Y. Gal, and S. Levine. Learning invariant representations for reinforcement learning without reconstruction. Arxiv preprint Arxiv 26-1742 2020. M. Kemertas and T. Aumentado Armstrong towards robust bisimulation metric learning. Advances in neural information processing systems 34-447-16477 2021. C. Galata, S. Kumar, J. Buckman, O. Naam, and M. G. Bellamere. Deep MDP, learning continuous latent space models for representation learning. In International Conference on Machine Learning, pages 2170 to 2179. PMLR 2019. L. Zhao, Y. Wang, L. Yuan, J. J. Sun, F. Schroff, H. Adam, X. Peng, D. Metaxas, and T. Liu. Learning view disentangled human pose representation by contrastive cross-view mutual information maximization. In proceedings of the IWLP CVF Conference on Computer Vision and Pattern Recognition, pages 12793-20802, 2021. A. Radford, J. Wu, R. Child, D. Luan, D. Amode, I. Sutskever et al. Language models are unsupervised multitask learners. OpenAI blog 189, 2019. K. Esslinger, R. Platt, and C. Amato. Deep Transformer Q Networks for Partially Observable Reinforcement Learning. Arxiv preprint Arxiv 2206-0178 2022. Tini, Emma B. Eisenbach, and P. L. Bacon. When do transformers shine in RL? Decoupling memory from credit assignment. Advances in Neural Information Processing Systems 36, 2024. Tini, B. Eisenbach, and R. Salakutinov. Recurrent model-free RL can be a strong baseline for many POMDPs. In International Conference on Machine Learning, pages 16691 to 16723. PMLR 2022. Deha and J. Schmidhuber. World Models. Arxiv preprint Arc 313, 2018. L. Zintgraf, K. Schiarlis, M. Eagle, S. Schultz, Y. Gal, K. Hoffman, and S. Weitzen. Veribad, a very good method for Bayes adaptive deep RL via meta-learning. In International Conference on Learning Representations ICLR 2020. C. C. Hung, T. Lillicrap, J. Abramson, Y. Wu, M. Mirza, F. Carnavale, A. Ahuja, and G. Wayne. Optimizing agent behavior over long time scales by transporting value. Nature Communications 10, 1, 1-12, 2019. E. Z. Liu, A. Raghunathan, P. Liang, and C. Finn. Decoupling exploration and exploitation for meta-reinforcement learning without sacrifices. In International Conference on Machine Learning, pages 16925 to 6935. PMLR 2021. D. Barber and F. Agakov. The IM algorithm, a variational approach to information maximization. Advances in Neural Information Processing Systems 16 on 320, 201, 2004. R. E. Wang, M. Everett, and J. P. Howe. RMAD-PG for partially observable environments and limited communication. Arxiv preprint Arc 2002.06684, 2020. J. Yang, A. Nake, D. Isla, K. Fumura. CM3, Cooperative Multi-Goal Multi-Stay Agent Reinforcement Learning. Arxiv preprint Arxiv 09.05188, 2018. J. Forster, G. Farquhar, T. Afuris, N. Nardelli, and S. Weitzen. Counterfactual Multi-Agent Policy Gradients. In proceedings of the AAAI Conference on Artificial Intelligence, Volume 32, 2018. R. Lowe, Y. I. Wu, A. Tamar, J. Harb, O. Peter Abil, and I. Mordach. Multi-Agent Actor Critic for Mixed Cooperative Competitive Environments. Advances in Neural Information Processing Systems 30, 2017. S. Lee, Y. Wu, X. Kai H. Dong, F. Fang, and S. Russell. Robust multi-agent reinforcement learning via Minimax Deep Deterministic Policy Gradient. Weishao, X. Liu, and Ciamato. Local Advantage Actor Critic for Robust Multi-Agent Deep Reinforcement Learning. A. Shi, L. M. Bhamadipati, E. Z. Long, S. Levine, and C. Finn. Learning to Explore in POMDPs with Informational Rewards. S. Seong, S. W. D. Shu, and W. S. Lee. Planning Under Uncertainty for Robotic Tasks with Mixed Observability. H. H. Nguyen, A. Bizero, D. Klee, D. Wang, R. Platt, and Ciamato. Equivariant Reinforcement Learning Under Partial Observability. D. Wang, C. Kohler, X. Zhu, M. Jia, and R. Platt. Bulletarm, an open-source robotic manipulation benchmark and learning framework. D. Wang, R. Walters, X. Zhu, and R. Platt. Equivariant Q-Learning in Spatial Action Spaces. H. Van Hasselt, A. Guise, and D. Silver. Deep Reinforcement Learning with Double Q-Learning. T. Harnoja, A. Zhao, P. Abil, and S. Levine. Soft Actor Critic, Off-Policy Maximum Entropy Deep Reinforcement Learning with a Stochastic Actor. T. Ney, B. Eisenbach, E. Salehi, M. Ma, C. Gehring, A. Mahajan, and P. L. Bacon. Bridging State and History Representations, Understanding Self-Predictive RL. K. Cho, B. Van Mariembor, C. Gulchera, D. Bodenau, F. Bugaris, H. Schwenk, and Y. Bengio. Learning Phrase Representations using RNN Encoder-Decoder for Statistical Machine Translation. M. Hausnecht and P. Stone. Deep Recurrent Q-Learning for Partially Observable MDPs. Vimni, A. P. Badia, M. Mirza, A. Graves, T. Lillicrap, T. Harley, D. Silver, and K. Kavakchuoglu. Asynchronous Methods for Deep Reinforcement Learning. K. Perlin, Improving Noise, D. P. Kingma and M. Welling, Auto-Encoding Variational Bayes, J. Schulman, F. Wolski, P. Dariwal, A. Radford, and O. Klimov, Proximal Policy Optimization Algorithms, D. Wang, R. Walters, and R. Platt, SO2 Equivariant Reinforcement Learning, Details of Agents DTQN TSAC, ZPDRQN ZPRSAC, BA TSAC, UA TSAC, BDQN BSAC Hyperparameters, Network Structures, Details of Domains Sphinx, Carflag 2D, Heaven Hell Robot Domains Representations, Training Data Generation, Network Architecture, Mutual Information Estimation, Minimizing ISO, Maximizing IOO, and ISS Hyperparameters. Additional experiments using ZSIZ over ZS for task learning, using only auxiliary task intrinsic rewards, using GRU versus GPT, visualization of intrinsic rewards. Details of hardware experiments obtaining depth images, added Perlin noise for better sim-to-real transfers. Details of O2 rotational data augmentation. Details of agents DTQN, TSC are variants of DQN and SAC, made memory-based by using a transformer as the sequence model. Similar models have been explored in previous work. ZPDRQN, ZPRSAC are similar to DTQN and TSAC, except they use a recurrent sequence model instead of a transformer. Using a recurrent sequence model, GRU, is required. Additionally, these agents are regularized with a self-predictive auxiliary task of predicting the next latent state Z from a history H. The auxiliary task aims to minimize laux equals I g that phi h a minus f phi h pre 2, where f phi is the target network of phi. BA-DTQN, BA-SAC leverage state availability differently during training. In BA-DTQN, a state-based critic QSA and a history-based critic QHA are learned. However, during execution, when no state is available, QSA cannot be used. Encoder transformer MLP history-based critic encoder MLP state-based critic encoder. Concat QA is not mathematically well defined and is generally a biased estimate of QHA, which is used to select actions during execution. The difference between B8SAC and TSAC is that the critic is trained additionally using state input during training. Specifically, we learn a state-based critic QA instead of the history-based QHA. Similar to BA-DTQ and BA-TSAC also has bias. For BA-TSAC, during execution, actions are computed using a history-based actor. In UA-DTQN, a history state-based critic QHSA and a history-based critic QHA are learned. Unlike BA-DTQN with QA, QSHA can be well-defined and has been proven to be an unbiased estimate of QA. During execution, actions are selected using QHA. Unlike B8SAC, UASAC combines both state and history features to train the critic, i.e., we learn a history state-based critic QSHA. Similar to UA-DTQN, UA-TSAC does not introduce learning bias. During execution, actions are computed from a history-based policy. The architectures of these agents are depicted in Fig 14. These agents are based on Believer, which leverage the state availability to train an agent in 3 stages. Stage 1, learning compact state representations with state-labeled transitions, i.e. a batch of samples, SOAR-SO. This stage is similar to our first stage, but without the information-based regularizations. Instead, the authors propose to regularize the KL divergence KLFS N01 to avoid overlapping features between FAS and FO by giving penalty when encoder transformer MLP UA DTQN, encoder history state-based critic, history-based critic, encoder transformer MLP encoder concat, architecture of UA DTQN. Encoder transformer encoder MLP UA TSAC encoder transformer encoder MLP encoder history-based actor history state-based critic. Concat architecture of UA TSAC. EverFS is used to derive features. This, however, does not avoid the overlapping issue between learned state and observation features, as shown in our experiment. Stage 2. Learn a recurrent history model PFIH with variational autoencoders by maximizing the joint log likelihood PFISH averaged over samples. Stage 3. Use the history module P4H for task learning. First, samples are drawn from the VAE to derive a history summary. Then, this summary is used as the states for task learning using memoryless RL algorithms. The authors optionally fine-tune FIDA-H with the on-policy data. As the original paper applied their method for PPO, which is on-policy, we had to modify the method to apply to DQN and SAC, resulting in BDQN and BSAC. In Stage 2, to fairly compare with other baselines, we replace GRU in the history model with the GPT model used in other baselines. Moreover, in Stage 3, we fine-tune the history module for every domain as used in the original code. Finally, the sequence model of BSAC is shared between the actor and the critic, following the original code. BDQN encoder MLP history-based critic transformer, pre-trained history encoder concat transformer encoder MLP encoder. MLP BSAC history-based critic pre-trained history encoder MLP history-based actor concat architectures of BDQN and BSAC with a pre-trained history encoder from Believer. We changed the history encoder from view-based to transformer-based for a fair comparison with other agents. For BSAC, we use a shared history module, similar to the original code. Hyperparameters for DDQN, we use an epsilon greedy exploration strategy with a linear schedule, starting at epsilon equals 1.0 and ending at epsilon equals 1t, with t being the episode length. The schedule time is equal to 10% of the total training time steps. We use a batch size of 64 episodes. For continuous actions, we use SAC. We automatically tune the entropy temperature, initializing at 0.01. The chosen target entropy is equal to the negation of the action dimension. We use the discount factor gamma equals 0.99. We use a batch size of 64 episodes. Other hyperparameters are in Table 2, with shared parameters and one specific for each agent. Hyperparameters used for RL agents. Agent hyperparameter value, shared among all agents, episode length 50, discount factor 0.99, replay buffer size 1M, grid world domains 100K, robot domains target update rate 0.005, actor learning rate 3E4, critic learning rate 3.5 for CF and S, 3.4 for other. Batch size 64 SAC, initial entropy temperature 0.01, update per step 0.25 for discrete domains, 1.0 for robot domains, ZPDRQN loss weighting 1.0 for discrete domains, 0.1 for robot domains, Rs loss weighting 0.5 for all domains, reward weighting 10.0 for HHS, 12.1 for robot DO for CFBDQN, BSAC latent dimension 32xDim16 ZDim16. Network structures FCN, a fully connected layer with N outputs. Conv, a convolutional layer with filter size FPESF and stride S. R, the ReLU activation function. Max pool W, a max pooling layer with window size W. TH NHSD, transformer with H heads, N layers, hidden size HS, and the dropout rate D. GRU NHS, GRU with N layers and hidden size HS. FC64 observation encoder, action encoder, top branch F64, plus R observation encoder sequence model trans 21128 0.1, GRU 1128 or bottom branch FC128 plus RFC32. Network structures used in Heaven Hell, FC64 plus R observation encoder, action encoder, top branch observencoder sequence model trans 21128.1, 128 or 64 car max pool 2 128.21 plus R max pool 2 256 conv 21 plus R flatten FC32 bottom branch 16 conv 132 conv 2 R flatten FC100. Network structures used in car flag 2D observation encoder bottom branch 64 conv 21 car 128 conv 21 plus R max pool 2 256 conv 2 plus R flatten FC32 FC64 plus R observation encoder. Action encoder, top branch sequence model trans 21 128 0.1 GR1 128 or 16 conv 21 plus R32 conv 21 plus R flatten FC 100. Network structures used in Sphinx. Observation encoder. Bottom branch 32 conv 84 plus R64 conv 44 plus R31 plus R flatten FC 64 plus R. Observation encoder. Action encoder, top branch sequence model trans 21 128.1 GRU1 128 or 16 com1 plus R32 conv 21 plus R flatten FC 100. Network structures used in robot domains. Details of domains: Sphinx observation channel 0, channel 1, state channel 0, channel 1 Sphinx domain with two-channeled pixel-based observations and states. Channel 1 of the observation reveals the goal cell, green, only when the agent enters the blue cell. In contrast, the same channel of the state always reveals the goal cell regardless of the agent's position. In this domain, an agent must visit the goal cell, which can be in one of three corners, except the top left one. The agent must visit the information cell, blue, at the top left corner to know the current corner of the goal. However, there is a cost when going to the information cell. Action: move right, move left, move up, move down. Observation: a 6x6x2 image with the first channel encoding the agent's position and the second encoding the goal's position. The second channel only contains the goal information when the agent enters the blue cell. State: a state has the same structure as an observation, but the second channel always contains the goal information. Reward: +1 when reaching the goal, -0.2 when visiting the information cell, and 0 otherwise. Car flag 2D channel 0, channel 1, channel 0, channel 1. State observation, car flag 2D domain with two-channeled pixel-based observations and states. Channel 1 of the observation reveals the goal cell only when the agent enters the blue region. In contrast, the same channel of the state always reveals the goal cell. In this domain, an agent must visit the goal cell, green, to finish the task. The goal cell, however, is only present in the observation when the agent visits the information region, blue. Action: move right, move left, move up, move down. Observation: an 11x11x2 image with the first channel encoding the agent's position and the second encoding the goal's position. The second channel only contains the goal information when the agent enters the blue region. State: a state has the same structure as an observation, but the second channel always contains the goal information. Reward: +1 when reaching the goal and 0 otherwise. Heaven Hell. In this domain, an agent must visit Heaven, green cell, to finish the task. The goal cell can be either on the left or on the right side with 50% probability. To observe the side of the goal, left or right, the agent must visit the priest, who resides in the bottom right corner. Action: move right, move left, move up, move down. Observation: a vector consists of the agent's position and the side information. The side information can take the value of 0, no information, 1, heaven on the right, or -1, heaven on the left. State like the observation, but the true side of the goal is always revealed. Reward: +1 when reaching heaven, -1 when reaching hell, and 0 otherwise. Robot domains. In these domains, the agent must manipulate the only movable object among two objects, which are exactly the same under the top-down depth image observation. Action: an action A equals deva x, viva y, dz that are, where dx, the y, and 0.00.05 are the displacements of the gripper in the xyz axes, and $, 0.8 is the angular rotation around the z-axis. Observation: all robot domains share the same observation. The top-down depth image taken from the camera centered at the gripper's position. 2 fingers of the gripper are projected on the image. State: the state also has 2 channels. The first channel is the first top-down depth image of the observation. While the second channel of the observation is non-informative, the second channel of the state is an image that masks everything except the movable object, see Figure 22, in which the movable objects are colored red for visualizations. Reward: in block pulling, the agent receives a reward of 1.0 only when the 2 blocks are in contact. In block pushing, the agent receives a reward of 1.0 only when the movable block is within 5 centimeters from the center of the goal pad. In drawer opening, the agent receives a reward of 1.0 only when the unlocked drawer is opened more than 5 centimeters. State observation channel, channel state observation channel, channel observation, state channel, channel visualization of an observation and a state in block pulling, block pushing, and drawer opening. The movable object is the red one. The state and the observation have two channels, the first being the top-down depth image. In block pulling, the second channel of the state reveals the movable object and the gripper. In block pushing, the second channel reveals the movable block, the gripper, and the goal pad. In drawer opening, the second channel in the state reveals the unlocked drawer and the gripper. Training data generation. In these domains, a uniform random agent generates training samples, each consisting of a transition, state, observation, action, reward, next state, next observation. The robot domains utilize 80 episodes for demonstrations during task learning. The training data is augmented with random rotations per transition, as described in 49. The planners used in creating demonstrations are as follows. Block pulling planner randomly selects a block and attempts to pull it towards another block until the task is completed. If the selected block's position remains unchanged for a period, the gripper is moved to the other block to continue pulling. Block pushing planner randomly selects a block and pushes it towards the goal pad. If the block's position stays unchanged, the gripper is shifted to the other block to resume pushing until completion. Drawer opening planner randomly selects a drawer and tries to open it. If the chosen drawer fails to open, the gripper moves to another drawer and repeats the opening action. Network architecture. The specific architecture for learning representations is displayed in Fig 23. The components for each domain are described using acronyms. FCN, a fully connected layer with N outputs. ConvF-S, a convolutional layer with filter size FTFF and stride S. ReU is the activation function. MaxPool-W, a max pooling layer with window size W. Mutual information estimation. To minimize ISO, the variational estimate is computed as follows based on EQ2, with the upper bound equation, LCLB equals 1 log 2, water equal 1 C and log Q is of TDS. Convolutional layer with 64 filters of size 2 by 1 followed by ReLU activation. Another convolutional layer with 128 filters of size 2 by 1 followed by ReLU activation, and then a max pooling layer of size 2. Then, a convolutional layer with 256 filters of size 2 by 1 followed by ReLU activation. Next, the features are flattened and passed through a fully connected layer with 32 units. This is followed by an observation encoder, state encoder, and an FC layer with 16 units. Then an action encoder followed by 2 FC layers with 256 units each, and ReU activation. Subsequently, 3 FC layers with 256 units each and ReLU activation. These are followed by a dynamics model with an FC layer with 1 unit for reward prediction, then an FC layer with 32 units for predicting the next state features, and another FC layer with 32 units for predicting the next observation features. Convolutional layer with 64 filters of size 2 by 1 followed by ReLU activation and a max pooling layer of size 2. Then a convolutional layer with 128 filters of size 2 by 1 followed by ReLU activation and another max pooling layer of size 2. Next, a convolutional layer with 256 filters of size 2 by 1 followed by ReLU activation. Features are then flattened and passed through a fully connected layer with 32 units. An observation encoder, state encoder, and an FC layer with 16 units are next in line. This is followed by an action encoder, 2 FC layers with 256 units each and ReLU activation, and 3 FC layers with 256 units each and ReLU activation. Then dynamics model with an FC layer with 1 unit for reward prediction. Next, an FC layer with 32 units for predicting next state features, and another FC layer with 32 units for predicting next observation features. FC layer with 128 units and ReLU activation followed by another FC layer with 128 units and ReLU activation. Then an FC layer with 32 units. An observation encoder, state encoder, and an FC layer with 16 units. This is followed by an action encoder, 2 FC layers with 128 units each and ReLU activation, and 3 FC layers with 128 units each and ReLU activation. Finally, an FC layer with 1 unit for reward prediction, an FC layer with 32 units for predicting next state features, and an FC layer with 32 units for predicting next observation features in the dynamics model. convolutional layer with 32 filters of size 8x4, followed by ReLU activation, then a convolutional layer with 64 filters of size 4x4, followed by ReLU activation, followed by another convolutional layer with 64 filters of size 3x1, followed by ReLU activation. Then, the features are flattened and pass through a fully connected layer with 32 units. This is followed by an observation encoder, state encoder, and an FC layer with 16 units. An action encoder, 2 FC layers with 256 units each, and ReLU activation, and 3 FC layers with 256 units each, and ReLU activation follow. Finally, a dynamics model with an FC layer with 1 unit for reward prediction, an FC layer with 32 units for predicting next state features, and an FC layer with 32 units for predicting next observation features in robot domains. The variational distribution QoZS is updated to minimize the KL divergence between QoZS and PUS. We assume QoZS follows a Gaussian distribution and use the following network architectures: mean net F32R FC32, log variance network FC32R FC32 TANCH. We use a batch size B equal 500 and a learning rate of 0.01 for all tasks, except Heaven Hell, which uses a learning rate of 0.0003. We update Q whenever we update FUF and PSO. Maximizing IOZO and ISZS uses the following layers: layer N, layer 1, layer 0 state encoder, layer 1, layer N, layer 1, layer 0 observation encoder, layer N, layer 1. The architecture in Figure 28 calculates CSS and CISO-EO using a dot product operation. From the lower bound equation EQ3, we minimize the following loss: LDI to the 1 by B or B1, B SPJ EXI sub plus XJ EXI 8. The discriminator C uses the same architecture of the state encoder 5 when calculating the state feature ZS LOFS, and the observation encoder PES when calculating the observation feature ZO LOFO. We use dot product to compute SOS equals ZSLZO, E equals ZOL ZO. Hyperparameters used for training representations are provided in Table 3, including HH, S, CF, BPs, DO. Additional experiments using ZS versus ZS for task learning. Continuing the experiment from Section 5.2.1, we report the performance using ZS and ZS for task learning in all domains. Environment, step 0.75, might 0.50, 0.25, 0.00, 0.25, 5.75, 1.00. Return ZS only, A Sphinx environment, step 0.0, 0.1, 0.2, 0.3, 0.4, return ZS only, B. Car flag 2D environment, step 0.0 or 0.2, 0.46, 0.8, 1.0, returns only, C. Heaven Hell environment, step 0.0, 0.0, 0.2, 0.2, 0.4, do 1.0, return ZS only, D. Block pulling environment. Step 0.0, 0.20, 0.6, 0.8, return ZS only, E. Block pushing environment. Step 0.20, 0.4, 0.88, return ZS only, F. Drawer opening, using only auxiliary task intrinsic rewards. Here, we show the learning performance when using intrinsic rewards and/or the auxiliary task. Environment, step 0.75, 90, 0.50, 0.25, 0.0, 0.25, 0.5, 0.75, 1.0, return intrinsic only, auxiliary plus intrinsic. A Sphinx environment, step 0.0, 0.24, 4.6, 0.8, return intrinsic only, auxiliary plus intrinsic, B. Car flag 2D environment, step nata 0.50, 12, 0.20, 0.25, 0.75, 0.7, 1.25, return intrinsic only, auxiliary plus intrinsic, C. Heaven Hell environment, step 0.00, 2.4, 4.6, 0.8, 1.0, return intrinsic only, auxiliary plus intrinsic, D. Block pulling environment, step 0.0, 0.2, 0.4, 4.6, 0.8, 1.0, return intrinsic only, auxiliary plus intrinsic, E. Block pushing environment, step 0.0, 24.6, step 1.0, return intrinsic only, auxiliary plus intrinsic, F. Drawer opening. Comparing using intrinsic rewards or the auxiliary task versus using both. Using GRU versus GPT, we report the performance in all domains when applying them as the sequence model in our proposed agent. Figure 31, task learning performance when using a GRU versus GPT. Visualization of intrinsic rewards. We visualize the intrinsic rewards of trained agents in 3 grid world domains in Fig 32. The intrinsic rewards peak when the agents perform the information gathering actions. Details of hardware experiments, obtaining depth images, We fused the point clouds from two RealSense D455 cameras, Cam 1 and Cam 2, and one Azure Connect camera, Cam 3, to create an integrated point cloud to create a depth image observation. Examples of observations in the three robot domains can be seen in Fig 34. Orthographic projection. We fused the point clouds from three cameras and performed an orthographic projection at the gripper's position to create a depth image observation. Examples of observations in real robot experiments. Added Perlin noise for better sim-to-real transfers. Following, we found it useful for better sim-to-real transfers by adding the Perlin noise to the depth images during training for more robust policies by being closer to real-world depth images. For all robot domains, we applied the noise with a magnitude of 7 millimeters. Block pulling before, block pushing before, drawer opening before, block pulling after, block pushing after, drawer opening after. Depth images before and after adding Perlin noise for better sim-to-real transfers. Details of SO2 rotational data augmentation. We perform SO2 rotational augmentation by choosing a random angle and rotating the depth images around its center. We perform this augmentation in two cases, when learning the representations to utilize the data better. For each transition SOARSO, we sample a random angle and rotate SOSO at the same angle. Each transition has its own random angle. When performing task learning in robot domains, given an episode, we first sample a random angle and apply the rotation with this angle for every state, observation, next state, and next observation within the episode. Because we are trying to learn a history-based policy, this is to ensure the augmented history is valid. Examples of rotation data augmentation applied for transitions in an episode in block pushing to augment the data for learning the representation. A different random rotation is applied independently for each state, observation, next state, and next observation in each time step in an episode. Examples of rotation data augmentation applied for an episode in block pushing. The same random rotation is consistently applied to every tuple state, observation, next state, and next observation within an episode.